Long ago, there was a frightening creature called Mdp, the most dangerous parker, whose name alone sent shivers down spines. Those who crossed the path were left trembling in fear, unable to shake off the terrifying memories of its presence. The Mdp is here. Amidst a sea of challenges, it's our time to face the monster. How can we defeat it? Our journey begins with the eyes of the vehicle.
Image recognition is handled by me, Tony, and Iris. So we use YOLO BA as our object detection AI model and RoboFlow to annotate our data set. Especially, we annotated half of the image just in case our camera was not centered. So since the inference of images will take time, the Pi does not wait for the detected results to be written, but instead will continue driving on its path. The results will be written later after the laptop is done with the inference.
At the heart of our prototype is the Raspberry Pi.
Working on the Raspberry Pi, my responsibilities lie in integrating the algorithms, robot movement, Android communication, and image recognition. Let's look at how we did it. The Raspberry Pi is physically connected to the Pi camera, where photos can be captured for recognition. Once captured, the photo is sent to the laptop for image recognition through a flash server. The recognized value is then passed back to the algorithm. The algorithm is hosted and computed on the Raspberry Pi itself, and the movement commands are sent to the STM32 through an abstraction layer using UART, where the robot then moves accordingly. Map, setup, and the start trigger is done on the Android tablet, and the data is sent between the Raspberry Pi through Bluetooth Classic. Time for a side quest. We found it difficult to mount the cameras and sensors on the robot and wanted something more elegant than using tape or blue tack, so we turned to 3D printing to design custom mounts. We iterated through 3 camera holder designs and finalized with one that resembles the air intake of an F1 car. The design also took into consideration cable management, which we will see later. For the ultrasonic and IR sensors, we originally went with a front and back mount, but later side mounted them to complete task 2 with greater accuracy. Every car needs a car plate number, so we designed one to be mounted on the back of the car. Finally, we explored exotic options for mounting a laser for better alignment at the start of the run, but later realized it interferes with image recognition.
The right brain of our operation.
Before starting with the algorithm, we have multiple factors that will affect the car's movements. Examples include the arena borders, the obstacle positions, and the car's turn radius. This shall determine the validity and cost of the path from the path-finding algorithm.
The algorithm has 2 parts, Hamiltonian path and A-star search. The Hamiltonian path visits each vertex exactly once to find the shortest path by exhaustive search through all permutations. A-star search generates the optimal path from point A to point B by exploring all possible paths to the obstacle, assigning cost based on distance, and repeating until all obstacles are visited exactly once.
Our project's left brain.
Now I'll be talking about the STM32 component. On top of the standard and necessary features such as the IR sensor and ultrasonic sensor, our team also implemented various interpolation schemes and filtering to derive an absolute yaw value from the IMU, such that runtime angular corrections could be done with a PID controller. This was in part due to the magnetometer that couldn't be used due to high magnetic interference from the motors. Our team also implemented the STM32 code in C++ to utilize zero-cost abstractions to improve software modularity and reusability. Similarly, the UART command scheme between the RPi and STM32 was wrapped with functional and concurrency-oriented abstraction layers, which improved the ease of use and reliability. For instance, we introduced a binary exponential back-off retransmission scheme to ensure reliable execution of commands.
The hand of our project.
The Android is used as a remote controller. It is designed to have a simple and intuitive interface.
The landscape orientation of the app efficiently utilizes screen space with arrows on the left and chat, map, and challenge on the right for seamless navigation and communication. This placement aligns with user expectations, enhancing interaction ease.
There is a 20 by 20 grid map to plot obstacles and the robot setting point. To plot obstacles, simply tap on the cell. Removing obstacles is done by dragging it out of the map. The action controller can move the robot manually. It has forward, backward, left, and right buttons.
Switch on the change obstacle toggle and tap on the obstacle to change the obstacle direction and assign an ID.
The save map will save the obstacles plotted to the corresponding maps available. The save map can be loaded conveniently by selecting from the drop-down list. This streamlines the obstacle placement process. The start button under image recognition will get the task started. It will enable the timer to track the duration of the task. All in all, this app offers a streamlined and intuitive interface in landscape orientation.
Day and night, the team plans and prepares for the upcoming challenge.
Hey, can we save the picture? Why? Huh?
This one.